me minimize this. Hold on. Open it. Paint. Actually, I think that might be one of my problems is that I'm using paint. It messes up my bamboozle. Or my bamboo, whatever you call it. Is this where you want to begin? Number 9?
Yes, sir.
And what is the question? Graph it?
Yes, sir.
Okay.
I have some notes, so.
Well, I think we can have a look at this. I think I might be able to figure this out. What we want to do is, first of all, there's a couple ways you can graph.
Yes.
You can let theta go from minus 2 pi to plus 2 pi and plot points for r.
Okay.
And that's one way to graph it. Do you know what I mean by that?
Yes, sir. I think so.
Okay, I'll tell you what, let's do it. Let's just make a quick table here. And I'll show you what I mean. I'm going to use this one over here. So this is theta. And I'm going to start, let's start with 0.
Okay.
So what is r going to be when theta is 0?
R will be -12.
Okay, what's cosine of 0?
Oh wait, R will be 4.
Correct. Now let's let theta be pi over 6.
All right.
Come up with just an approximate number. I don't think we have to be super exact here. You can convert it to a decimal if you want.
Okay. So it's going to be 12 over 3 root 3 minus 2.
Yeah, why don't you go ahead and give me a number on that. It'd be easier. Like I said, we don't need to be super exact since we're graphing it.
So approximately 5.15.
Okay. And how about pi over 4? And then pi over 3, and then pi over 2. Let's go through one full quadrant.
All right.
Pi over 4 shouldn't be too bad because both cosine and sine are root 2 over 2.
That's right.
It should be just a negative root 2 over 2, which should be 24 over
root 2.
Yeah. Does that come out to be? I think it's negative, isn't it? Yeah, it's got to be.
I get positive 16 for 24 over root 2. Positive 16.9.
Hold on. Cosine is root 2 over 2. Sine
That's
is
right.
root 2 over 2.
Oh, yes, that is
I've got
negative.
3 of those minus 4 of them. That's got to be negative.
Yes.
So, whoops. I gotta be careful on this. It's really easy to erase. So do you get a number?
So would it just be negative 16?
Is it 16? We're going to end
So
up with a negative root 2 over 2 in the bottom. Flip and multiply. I got 24 over, okay, 16 sounds about right. Negative 16.
Yes, sir.
Okay, we'll just leave it like that for the moment. Root 3. I mean, pi over 3.
All right. So that's just going to be 3 over 2.
So that is root 3 over 2 minus 4 times 1/2, right?
Yes, sir. So is that negative 6.12?
I don't know. You're the one with the calculator. I'm not doing the math here. I thought you were doing it on your end.
Yes, sir, I am.
Okay, so what is it?
I think it's negative 6.12.
And finally, pi over 2.
All right. So we have
3.
so that yes, 3.
Okay, negative 3, right?
Yes, negative 3.
Yeah, because it's 0 minus. Okay, so now what we're going to do, and I'm going to do this not on your curve, but on one that I draw, because if I scroll down here, I lose what I've written. So I'm going to lay out a curve here. And you're aware that polar can be graphed on an xy coordinate plane. And in fact, any point that I put on here can have polar coordinates or it can have xy coordinates.
Yes, sir.
Okay, so let's do the first point. When theta is 0, meaning when the line is on the x-axis, r is a positive 4.
All right.
That point is on the graph. Do you see that?
Yes, sir.
When theta is pi over 6, which is 30 degrees, r is 5.15. That point's on the curve. When theta is 45 degrees, theta is r is minus 16, which means we have to go backwards. You understand that about polar?
Yes, sir.
I mean, you understand how to graph a polar coordinate?
Yes, sir.
Okay, good. And when theta is 60 degrees, r is about right there.
Okay.
Maybe a little lower. Here, let me bring that down a little bit. Can't get it to erase now. Okay. And finally, when theta is 90 degrees, r is pi or minus 3. You see how I get that? In other words,
Yes, sir.
the angle first, and then if r is positive, you go forward on the ray. If r is negative, you go backwards on the ray.
Yes, sir.
Okay. So if I look at just the first quadrant and connect the dots, the question is, how do I get Well, I always thought you could just connect the dots. And what I was going to kind of do was something like this. But that's not correct because that point is not on there.
Mm.
So I got a problem here. Just for the heck of it, let's graph that on Wolfram Alpha so we can see what it looks like. And then let's see if we can figure out how to graph it in a different way.
All right.
So it's 12 over 3 cosine theta minus 4 sine. Okay. I'm going to have to close this out. That is a way to do it. I'm not quite sure what I did wrong there. I suspect that when I graph it on Wolfram, it'll let me know pretty easily.
Yes.
Because it's going to show me what that thing should look like.
Is there a specific key for typing in theta on Wolfram Alpha?
You can use X.
Okay.
In other words, R equals, and it's 12 divided by 3 cosine X minus 4 sine X. Let's see if that works.
I get what looks like
It looks like a cosecant type curve or a secant curve shifted. And that's the next thing we're going to do is notice that it graphed it based on the fact that it was XY coordinate plane. In other words, it didn't graph it as a polar. I'm not sure. Hold on a second. Let me see.
Oh wait, there was an extended keyboard. Okay, I think I can put in theta.
Yeah, I can actually put in theta here too. Let me put in theta and see if that gives me a different. I just put in theta like this. Maybe I need parentheses around it. And then it may recognize it as polar. Play it a little bit like this. Let's see if it changes. It did. Notice what that is.
Almost there.
Yeah, the very first thing it gave me was the polar plot, which is a straight line.
Okay.
Which is correct. And it agrees with what I was graphing. I just didn't realize I was looking at a straight line. What I mean by that is, here, let me draw just slightly on this. In other words, we started out with theta being 0. It's hard to see here. I can't zoom in on this graph. You probably have a better shot of seeing it on your calculator because you can zoom in a little bit. But the x-intercept right there, is r equal 4, which is what we got.
Okay.
The y-intercept, which is when theta, in other words, this was when theta equals 0, r equal 4. When theta equaled pi over 2, r was negative 3. And notice that that's the x-intercept and the y-intercept for that straight
Yes,
line.
sir.
At least I'm assuming it is. I can't see it up close, but it makes sense. The numbers on their graph are 50. So 4 is going to almost look like the origin. And
Yes, sir.
when we looked at a 45-degree angle, we got negative 16, something like that, which puts it there. And then when we looked at the other one that gave us a negative, all those points are on a straight line. So that is the equation of a straight line. So in reality, you can do it exactly like I suggested, which is,
Okay.
now you might have to plot through 2 pi. In other words, we only plotted through pi over 2, right?
That's right.
We only let theta vary from 0 to pi over 2. Had we let theta go from 0 to 2 pi and say plotted every 45 degrees, we would see a straight line.
Yes, sir.
As you go all the way around once. You may not, well, yeah, okay. So let's see if we can figure out how else to do this. Interesting. If I try to do this in a way different than making a table, in other words, if I try to convert this to a xy function instead of a polar function, let's talk about the conversion factors.
Okay.
R equals what?
R is the radius.
It's x equals r cosine of theta, correct?
Yes, x equals r cosine theta.
Y equals r sine of theta, and r squared equals what's r squared equal? Oh, x squared plus y squared. X squared plus y squared. And then theta equals the inverse tan of y over x, unless x is negative, and then it's the inverse tan of y over x plus pi.
Okay.
Remember that? So these four in fact, let me go ahead and write that in there because that's pretty important. That's if x is positive, and it's equal to the inverse tan of y over x plus pi if x is negative. With me?
Yes, sir.
Okay, so let's take this function and see if we can convert it to xy's instead of r's and thetas. So let's start by doing r equal 12 over, and instead of 3 cosine of theta is x over r, right?
Yes, sir.
So that's 3x over r. That's what 3 cosine theta is.
That's right.
Hold on, did I get the 3? Just a second, did I get the 3 in the right place? Cosine of theta equals x over r. Okay, I did. Minus 4 y over r. So far, so good?
Yes, sir.
Now, that r is I can put it in the numerator. So I get 12r over 3x minus 4y. I can cancel those out. Multiply both sides. I get 3x minus 4y equals 12. And I can see that that is a linear equation.
Yes.
Which I can solve for y and then put it in y equal mx plus b form. And I know exactly how to graph it. In fact, the really easy way to graph this is to let x be 0, and you can see the y-intercept's minus 3. Let y be 0, you can see the x-intercept is 4. So those are the only 2 points I need to graph this straight line that's up there.
I see.
Okay. So I think this is probably the easier way to do it.
I think so.
And the table. The table is pretty basic. It's kind of like when they say graph a function, you rarely anymore make an XY table, right? It's just not the way you do it. You usually start with a parent function and then do transformations or translations or something like that. So the amateur way is to make a table. I guess amateur is a good expression. So let's go do another one.
All right.
Only this time, I don't want to out yet, but let me minimize it. And
it's an r squared this time.
Yeah. Let's see. I got to reopen that file. Okay. So this time, let's just see if we can convert it.
Okay.
Could be a little tricky because we're dealing with cosine of 2 theta.
Yes.
The one thing that I can, well, it's all right. We can handle that. What should we do with cosine of 2 theta? First of all, what should we do with r squared?
X squared plus y squared.
Yeah. Oh, hold on. I forgot to do this. So x squared plus y squared equals 16, and we have a number of identities to use. Got cosine squared minus sine squared.
Should we do that one?
Well, I'm not sure. Cosine squared, we'll try it. One of the others might work a little better. Yeah, let's try one of the others because I'll only have to do one substitution.
All right.
In other words, the other ones use strictly a sine or a cosine.
Yes.
And
so that is.
What is it?
I think it's 1 minus 2 cosine squared.
I think it's.
Or is it?
I'm not sure. Do you have a?
Let me make sure.
Yeah, if you can look it up quick, because I hate to get it wrong. I think that the cosine squared one is 2 cosine squared minus 1. So I believe this is correct.
Yes, it's 2 cosine squared minus 1 and 1 minus 2 sine squared.
That's right. Okay. So now we're going to plug in sine squared is y squared over r squared. You know what?
Yes.
I'm going to go back and leave that as r squared.
All right.
No, that won't help. Let's see. Sine is y over r. So that's y squared over r squared. And now if I multiply both sides by r squared, I get something like this. Now I substitute x squared plus y squared. Okay, so I've gotten rid of the theta and everything but x and y.
Yes.
Let's move the y, the 32y squared, over to the other side. So I've got x squared plus 33y squared equals 16. Is that the equation of?
That is a circle.
An ellipse.
An ellipse, yes.
Yeah. And for it to be a circle, the coefficients would have to be the same under or next to the x squared and the y squared.
Right.
Now, if I want to figure out how to graph it, I got to get 1 on the right side, which means I got to divide everything by 16. So x squared over 16 plus 33 over 16 y squared equals 1. How are you familiar with ellipses, or do you need refamiliarizing them? In other words, there's the
maybe a little bit of refresh. Maybe a little refresher.
This ellipse is at the it has its center at the origin because there's no h or k. Okay, so let's talk the general equation of an ellipse. Hope I did the math right here. So the general equation of an ellipse at the origin is x squared over a squared plus y squared over b squared equals 1. That's for a horizontal ellipse. And a has to be bigger than b.
Yes.
That's why it's horizontal, because a squared is bigger than b squared. Now, what is a?
A is 4.
So that length would be 4. In other words, the radius would be 4 from there to there. What is b?
B is 4 again.
Now we got to get that 33. Got to deal with that.
Oh yeah.
And we got to get it in the divisor. So let me show you a neat little trick here.
Okay.
We know that much. Y squared has to be all by itself, and I'm going to make this look like this. Notice that's the same thing.
Okay.
So b is the square root of 16/33. Just like 4 was the square root of 16. In other words, a is the square root of that denominator. B is the square root of this denominator once I get y squared all by itself, which I've done. So I need the square root of that squared. which will give us 16. In other words, I think this is correct, okay?
Yes.
So what's the square root of that? That's about 4 over 5.5, something like that. Not quite 6.
So
So that's like 0.8. So that distance right there between those 2 points is 0.8.
okay.
And if that was our only goal, we've got everything we need to graph it. They did not ask for the foci. There are 2 foci, one of them about right there and one of them about right there. But the graph of the ellipse does not include the foci. The graph of the ellipse is strictly the circumference.
Yes, sir.
So I know how to do it now. I don't need the foci on there. If I did need the foci, C is the square root of a squared minus b squared.
Okay.
That would give me the distance between there and the foci. Something less than 4, obviously. In other words, if I was analyzing it as a conic section, where I would want to know where those foci are, those are the focus points.
Yes.
Okay. On to the next one, or is there anything else about this one we need to know?
On to the next one.
Okay, you want me to graph this in Wolfram just to convince us?
Sure. Are we able to graph it as an r squared?
Yeah, I can graph it as a polar. So r squared equals 16 cosine of 2 theta. Do this. R equals 16 cosine of 2. Sure how many parentheses I need here. That was it? R equals 16 cosine, or is it r squared equals 16?
R squared. R
R
squared.
squared equals 16. We'll see what this gives me. All right. Darn. Not any ellipse.
So I think that's called a rose curve.
Yeah, with 2 loops. It is called a rose curve. And that's the standard formula for a rose curve, I believe. Let me look it up. Yeah, this would be helpful if I have my polar graph open, or my polar part of the textbook. Huh.
So B is even.
Yeah, this is called a Lehman skate. Lehman skate. Or Leibniz skate. It's of the form r squared equals a squared times cosine 2 theta.
Okay, and the length of each petal is A. Because 4 times 4 is 16, and the petals are 4.
Yep.
Okay.
Yep. R squared equals a sine of 2 theta is also a Lehman skate. But the general equation of a Lehman skate is r squared equal a squared sine or cosine of 2 theta.
Yes, sir.
Now, why did I think it was an ellipse? Because when I converted it algebraically, I got the equation of an ellipse. Huh. Interesting. Why? I'm trying to think. I wonder if it has something to do with, I multiplied everything by r squared.
Mm,
I didn't do that right.
that's where I think we went wrong.
Yeah, let me just quickly write this out here. Hold on a second. This is plenty of whiteboard. Yeah, I think I canceled the r squareds instead of multiplied them together. So I get r squared equals 16 times 1 minus 2 sine squared of theta. So far, so good? Yeah, so all I did was replace cosine of 2 theta with its identity. And now I get r squared equals 16 minus 32 sine squared of theta. And now I get r squared equals 16 minus 32 y squared over r squared. Yeah, I did the arithmetic wrong here. If I'm going to multiply both sides by r squared, I don't get rid of that r squared. I turn it into r to the fourth equals 16 r squared minus 32 y squared. And then, of course, this is x squared plus y squared squared equals 16 times x squared plus y squared.
Mm.
And now I have everything in x and y. And it doesn't look anywhere near like an ellipse. So I just did the math wrong before. Unfortunately, it doesn't look recognizable either. In other words,
So it's just knowing the formula.
what's that?
So it's just knowing the formula.
I think, yeah, it's knowing that, in other words, that's the problem with some of these polars. Notice one other thing about this Lehman scale. It's not a function.
Mm.
That is the beauty of polar coordinates, is you can talk about things and it doesn't matter if they're not functions. If you're dealing in xy coordinates, it's very important to keep everything as a function. But once you get into some higher math, you can do things a lot easier. In other words, let's just talk about one thing, the equation of a circle, okay?
Yes, sir.
That's pretty complicated. Whereas that's the equation of a circle in polar.
Because that's just the radius.
Exactly. In other words, it's much easier to describe a circle in polar than it is in XY rectangular.
Yes, sir.
And that's one of the reasons that when I look at this answer I got down there, I'm not going to be able to take that answer and do much with it. It's not going to look familiar to me because I don't know what Lehman-scapes look like in XY coordinates. That's why when you study polar coordinates, they give you all of these exotic shapes like rose petals, Lehman scales, Archimedes circles, or Archimedes, whatever they're called. But they're all, cardioids, things like that. And the best way to handle those is to kind of recognize them from the polar function, not convert them like I did. The conversion works fine if it's a simple function, like a straight line. But as you can see with this one, after converting it to x and y, I don't know how to graph that. I would have to go to my graphing calculator to come up with a Lehman scale. In fact, well, no. Anyway, so let's proceed under those new guidelines where there's more problems on that page, I trust. In other words, let's see if we can recognize the function.
All right.
Okay. R equals 5 sine of 3 theta. That to me looks like a rose petal.
I think so.
Yep. Here's the standard equation of a rose petal. Hold on.
So B is odd, A is the distance of the petal, so it's going to go up 5.
Yeah, R equals A cosine of n theta, or R equals A sine of n theta. So that's what we're looking at, is that. We're looking at the second one there.
Yes.
And let's see. If n is even, the rose has 2 n petals. If
Yes.
n is odd, the rose has n petals. So in our case, n is odd, which means we have 3 petals. So we're going to have something looks like that, I think.
Yes, I think so. Goes up to 5.
I may have it slightly off. Here's what we can do to check. Is that point correct? What is R when theta equals 0?
Wait, does it go out to the right when it's a sine or a cosine?
I think I've plotted the cosine.
Okay, so for sine, it would just
In
go straight
other
up.
words, it's got to go through the origin. When theta is 0, we got to be right there, not out here at 5. The only way my graph would be correct is if it was R5 cosine of 3 theta.
Yes.
In other words, this one is the cosine. The sine one must look like, let's see, when theta is pi, when theta is pi over 6, R is 5. Correct?
Yes, sir.
So when theta is pi over 6, R is 5. So this thing must look like this. And let's see, when theta is pi over 3, it would be back, yeah, it's back there. Let's see, we got to get theta to be, hold on a second. Let's see, we know we have 3 petals. If I could figure out what this point is and this point, then I'll know how to draw the rest of this thing. So let's see. This point is going to be when that angle is pi, which means it has to be pi over 3. So when theta equals pi over 3, we're at 0. That's that second point. Let's see. When theta equals 2 pi.
What is it when
theta equals 2 pi over 3, we're going to be back at 0. Let's see. Theta. What were you going to say? I didn't.
what is it when theta is 90?
Well, that would be pi over 2, so that would be 3 pi over 2, which is -1. There you go. So when theta is 90, I've got -5 is my r. So I do know that's the other half. In other words, the other part of the loop's got to go like that, which means the third part must go like that. There's a little bit of symmetry to these things.
I see.
But the key was determining, that was a good question you had, is when theta is pi over 2, I can figure out that r is -5. And so that tells me where that pedal goes. I knew where that pedal went. The only place for the third pedal is where I drew it.
Yes, sir.
So I suppose that's probably when theta is 3 pi over 4. That's my guess. 3 pi over 4, that would mean 9 pi over 4. And pi over 4, no, I don't know. But I suppose the other way you can do this is just to know how the sine comes out and the difference in the cosine. If I replace that with cosine, then I believe my original drawing was correct.
Okay. I think it's probably the second one.
Well, this one is for cosine, and this one is for sine. Notice the difference?
Yes, sir.
It's like one is just rotated by like 45 degrees over the other one. But it has to do with whether those pedals fall on the axis or not. In other words, in the rose pedal using cosine, the first pedal is along the x-axis. In the rose curve using sine, the third pedal is along the y-axis.
Okay. Yes.
Okay. So
Yes.
let's look at number 12. We recognize that as what?
That is a circle.
Of radius 2. In other words, that point is 2, 0. R is 2 no matter where you draw your angle. R is 2. And R is always positive. So as I work my way around from 0 to 2 pi, I get the spokes of a wheel, and the outside of it is the circle. Okay, let's look at another one. Do I have any more on this page here? I don't think so. No, we did 11 and 12.
Yes, sir.
Okay. So what else do you need to know about polar? Anything specific? I'm not sure exactly what kind of, other than graphing them, like we've been doing. And you did actually discover a couple different ways to graph it. You can graph it using a table. You can graph it by converting it to XY and seeing if you recognize that. Unfortunately, most of these polar curves don't end up being simple functions at all. So that's a hard way to go. In other words, unless I did number 12. If I did number 12 and I converted it using the identities to convert between polar and rectangular, I would get x squared plus y squared equals 4.
Yes, sir.
Or I could just recognize that r equals 2 is the equation of a circle whose center is at the origin and whose radius is 2. There are some fairly sophisticated, and it only gets worse. When you get to Calc 3, you find out about the calculus of polar coordinates. And you know where polar coordinates are particularly valuable?
Where?
When you're analyzing the solar system.
Really? Like orbits?
Yeah, and the reason is that everything orbits the sun, where, in other words, the Earth orbits the sun in a elliptical path, and the sun is at one of the foci. In other words,
Oh, that's right.
if I draw an ellipse like that, here's the sun right there, and the Earth is right there, just going around the sun. But everything that orbits another body, the main body that is being orbited is always at the foci of the ellipse.
Yes.
And therefore, it's far easier to describe the motion of the planets about the sun using polar coordinates than it is using XY coordinates.
Yes.
So that's why they do it. That's why most motion in the universe is described by polar coordinates. And then what they do is they shift. In other words, normally if I drew an XY axis on that thing, it would be like that. But what they do is they shift the axis so it's right there. Then the math even gets easier still. But that is quite advanced calculus, and if you were, I'm not be ready to tutor that. I would have to refresh quite a bit.
Okay.
To be able to tutor that. Some of these other shapes you probably want to memorize. I guess, I don't know. You're going to be tested on these?
Yes, sir.
In a similar manner as what we just did. In other words, they're just going to give you a polar equation and they're going to ask you to graph it.
Yes, sir.
So you probably want to memorize that what cardioids look like, what circles look like, what straight lines look like, what Lehman scats look like, a lemacon without an inner loop or a lemacon with an inner loop.
Yes.
I
think not the only yes, I have notes on those.
Okay. Is I would suggest memorizing those. In other words, like when we came across that r squared equals a squared cosine of 2 theta.
Okay.
If you had the general formula for Lehman scat, however you pronounce that, you would recognize that that's a Lehman. You'd be able to draw it.
Yes.
How they look. And usually if you have a general idea how they look, in other words, I knew that a rose curve either looked like, in other words, it either looks like this, or the sine one looked like this. Now, I might forget which one is sine and which one is cosine, but you can always figure it out. This has to be sine because this point right there is when theta is 0. And
Yes.
tell that this got to be cosine, because when theta is 0, r is clearly 5. So this cannot be, this has got to be the cosine one.
Yes.
This has got to be the sine one. And you can figure out that by when theta is 0, r is 0 on the one on the right. That point right there is theta equals 0, r equals 0. So you can,
Yes, sir.
you can remember, you can distinguish between the two of them by just testing a point frequently.
Okay.
Okay. Yeah, I don't know what else to tell you about it. They
I mean,
must come into play in higher math.
yes, I think it's mainly just the memorization of the formulas, like you said.
Here's one that's interesting. R equals E to the theta over 5. That is Archimedes' spiral. In other
Yes.
words, every time theta increases, that circle increases. Now, what would the XY equation look like for Archimedes' spiral? I have no idea, nor do they ever even talk about it. In other words, once you have the polar equation, you don't go back. Yeah. Okay, I'm just going through my book here. Yeah, in fact, my book even has a comment about a calculus comment about how in polar coordinates does define. Oh, here's an interesting comment. In rectangular coordinates, r equals 1 is not a function, but in polar coordinates it is.
Okay.
In other words, there's no vertical line test for that, because r equals 1 is a circle. So we know it's not a function, but exactly what they say in this book is in polar coordinates, r equal 1, whose graph is also the unit circle, does define a function. And here's why. It's because for each choice of theta, there is only one corresponding value of r. That's what defines a function in polar coordinates. Just like in xy coordinates, for every value of y, you only have a single value of x, or I might have it the other way around. But that same verbal definition applies to polar, only instead of x and y, it's theta and r.
Yes, sir.
And then it says, since many uses of calculus require that functions be used, the opportunity to express non-functions as functions becomes extremely useful. Note also that the vertical line test for functions is valid only for equations in rectangular coordinates, not in polar. So you cannot use the vertical line test to determine whether this is a function or not in polar coordinates. And they are functions because for every value of theta, there is a unique value for r. Hold on. For each choice of theta, there is only one corresponding value of r when I have the polar equation r equals 1. And that's true. For every theta, there's an r.
Yes.
They're the same, but you can have that with xy also. In other words, you can have a lot of different x's produce the same y, and it's still a function. Passes the vertical line test.
That's right.
All right. You think you're good to go on polar?
Yes, sir. I think so.
Think of any other thing to talk about? I bet you have De Moivre's theorem coming up.
I know we've gone over that
You and I
sometimes
actually
in the
went over
past.
it last spring. You barely got into De Morse's theorem.
Oh,
But
barely.
that's where
Okay.
you take a complex number and express it in polar form.
Okay.
The cis function.
All right.
But anyway, we can talk about that next time if you want to.
Yes, sir.
All right.
All right.
Thank you. You're giving me a good refreshing on some of these subjects that I don't get a whole lot of work on,
Yes, sir.
like polar. So have a good
All
one.
right.
And let's see, our next session is going to be next Tuesday, right?
Yes, sir. It is.
And we're starting next week. We're going to be back on Tuesdays and Thursdays at 3:30 for an hour.
Yes, sir.
Okay. At least through
All right.
Thanksgiving. Yeah. Okay. I will let you go. Oh gosh, I forgot. I have a 4:30 today. I really got to let you go. I rarely have another session after you, but I do tonight. Bye bye.
All right. Bye.